Here we consider the last test within this module dealing with two populations. Here we are looking at the non-parametric alternative to the paired t-test, and the one we're going to use here is called the Wilcoxon signed rank test. And so the normality assumption, by the way, we can check this assumption by looking at, see here if I can get the pen to work. We can check this assumption by looking at the QQ plot, right? That gives us a sense of the reasonableness of the assumption of normality. Anyway, so we check that. We can check the differences, the QQ plot, and see, is it reasonable to assume that the differences come from a normal or a near normal population? And if it's not reasonable, then this Wilcoxon signed rank test may be an appropriate alternative. So what we're going to look at here for this test, now it still has assumptions. They're a little bit looser than the paired t-test. The assumptions for this Wilcoxon signed rank test are that the differences are independent of each other, and that the distribution of the differences is symmetric about the population median M here. Okay. Now, because of this symmetry assumption, it turns out that inferences made on the median are the same as inferences made on the mean. That's not quite the same thing as saying that this test is equivalent to the paired t-test, but it's saying that if you want to make an inference on the mean here, you can, because the median and the mean for these underlying populations are the same due to the symmetry assumption. The procedure for this test is as follows. You compute the difference, the differences for each pair. Then you subtract that difference from, subtract d naught from that difference. Now d naught here is the median under the null hypothesis. So under this, say this two-tailed test here, d naught is the value of the median, the population median M, under the null hypothesis. Okay, so we take each difference and we subtract off the null hypothesized median difference, and then what we're going to do is, if we have a Q that is 0, we're going to delete it, and then we're going to assign N as the number of non-zero Q's. In effect, we're ignoring the data where the Q's are 0. Okay, and then lastly, what we do is we take the absolute value of the Q and we rank the absolute value. We rank those pairs according to their absolute value of the Q quantity. Then we compute the following test statistic. Well, it's the pieces that will tell us what the test statistic will ultimately be. Here, this quantity T plus, which is the sum of the ranks that have positive Q's, and then this other quantity T minus, which is the sum of the ranks that have negative Q's. Okay, and so this is going to be our basis to make a decision about the median, the population median difference. Now here's our types of hypotheses that we can look at here. We can have a right tail test. Is the population median bigger than d naught? We could have a left tail test. Is the population median less than d naught? Or a two tail test. Is the population median different than d naught? Okay. Often d naught is simply 0. But our test statistic for this Wilcoxon signed rank test, when n is small, that is when n is less than or equal to 50, according to the book's rule of thumb, is defined as follows. It's called T. Now, just because it's called T does not mean it's a student's T test statistic, but this T test statistic here is defined to be T minus if we're dealing with this kind of right tail test. It's T plus if we're dealing with a left tail test, and it's the minimum of T minus comma T plus if we're dealing with a two-tailed test, okay, here in 3. Okay, and what we do is we reject the null if the T value is less, let's see, I got this out of order here, is less than or equal to the appropriate percentile from table 6 from the appendix, and that's this involves this particular distribution. There's this test statistic follows a distribution. We're not going to go into the background of how you get the distribution of this test statistic, but somebody else has done the work for us, and we have the appropriate percentiles, and all we need to do is compare our observed test statistic to the percentiles from the distribution to make a decision. Okay, so moving along here, a couple of notes here. If the data are tied, then the ranks for the tied data should be taken to be the average of the ranks. Okay, and we'll actually see this in our example where we have the situation where we have similar differences or the same differences for different pairs, and we need to take the average of the ranks in that situation. Secondly, here under note B, the mean of that T value turns out to be n times n plus 1 over 4. We're not going to derive where that came from. If you want to see where that came from, you would want to look at a course or a book in non-parametric statistics. Sigma squared T, it turns out to be n times n plus 1 times 2n plus 1 over 24. And I also want to make a note here to see the text for this sigma squared when there are tied ranks. Okay. All right. So I want to know the mean and the variance of T in the event that I can use a normal approximation. It turns out if I take T and subtract off its mean and divide by its standard deviation, this quantity Z here is approximately standard normal under the null hypothesis, and so I can use that to make a decision here. Now this is in the large sample case when n is bigger than 50. Okay. The way I think about the making a decision is for the 1 and 2 hypotheses on the previous page. I'm going to reject the null if Z is less than negative Z naught, and for the two-tailed or the case 3 there, reject the null if Z is less than negative Z sub alpha over 2. Okay. Now I make a note here to see table 618 for a comparative simulation study between the paired t-test and the Wilcoxon signed rank test. Basically, so after you look at that, you'll notice that under most situations, let me back up, when we're sampling from a normal population, the paired t-test tends to be more powerful than the Wilcoxon signed rank test. But in a lot of the other situations where you're sampling from a non-normal population, the Wilcoxon signed rank test has a little more power, or in some cases substantially more power. And so that's reason to use a Wilcoxon assigned rank test if there's strong evidence against normality for the paired differences. Okay, here is an example. Take a moment, read this example, get your bearings on it, understand the data, and maybe even try to work through this before you watch the rest of the video, but use the pause button right now. Okay, so if you want to work through this problem here, if you notice, what we first need to do is we first need to, well, let me back up. I want to look at the parameter of interest before actually, I want to identify the parameter of interest before we start to do any calculations. The parameter here is the population median difference between the firstborn, I'll say first and secondborn measurements. Okay, so I'm taking firstborn minus the secondborn, and so this is an effort to see, do firstborn twins tend to be more aggressive than the secondborn twin? Okay, but so I'm going to need the differences here. I'm going to look at d sub I, and well, let me d sub I, yeah, we can go ahead and do that. D sub I, the difference here, let's take the difference is going to be -2 there, -6 here, 1 here, 4 here, 91 minus 96, -5, difference of 0, 12, 1, 5, -9, 7, and 15. Okay, that's DI here. And what I'm going to do is I'm going to compute a Q for each of those. Now you recall Q, let's see, I want to get rid of that. Q is the difference minus the difference under the null. Okay, so let's set up the hypotheses here so we know what that would look like. Okay, so if I think about H naught and HA here, or H1, probably throughout these videos have been going back and forth, but the alternative hypothesis, you get the idea. We're checking to see here, we're just looking for an increase in the aggression score, and so we're measuring that according to the median. We're asking the question, is the median bigger than 0 effectively? So we're not looking for a threshold amount. The D naught as specified throughout the notes in this section is 0. Okay, so just to be clear here, the D naught is 0. And so what does that mean? That really means that the differences here are also just the Q's, because if for each difference the Q's here, well, yeah, the differences in the Q's are the same thing because I'm subtracting 0 there. Okay, so I've got that row, and the next thing I'm going to do is I'm going to make a row. What do I need to do next? I need to delete all 0 Q's and assign n as the number of non-zero Q's, and I'm going to also need the absolute value of Q, and then I'll rank that. And so let's see here, let's go ahead and make a row for the absolute value of Q here. Absolute value of Q is 2. Absolute value of negative 6 is 6. Absolute value of 1 is 1. 4, 5. Here I'm not interested in that. I'm tossing that 0 here. Absolute value of 12 is 12. This is 1, 5, positive 9, 7, and then 15. Okay, and now I want to rank these. Kind of out of space here, but I want to rank these. Alright, so if you look at the smallest difference, or the smallest absolute Q value, is 1. That's here. That's also over here, right? So what I'm going to do is, because I have a tie right off the bat. Up here under this note, we said if there's tied values, then the rank is the average of the ranks there. So let's do that here. So what I'm going to do, between these two pairs, I would have a ranking of 1 and 2, but because they have the same absolute Q value, I'm going to average 1 and 2, which is 1.5, and I'm going to give the rank of 1.5 and a rank of 1.5 to those two cells. The next largest value is 2 here, and 1 and 2 have already been used for the 1.5 cell and the 1.5 cell over here. So I'm going to have a rank of the rank value is going to be 3, and then the next largest value is absolute value of Q is 4, and so that's going to have a ranking of 4. The next value here, I've got 2 5s. I've got a 5 here and a 5 in this area here. So I'm going to have an average of the 5th and 6th rank, which is going to be 5.5. So those will share the rank of 5.5. And then I'm going to go up to a ranking of 7, which is going to correspond to this that absolute value of 6 there. And then I've got 7 here. It has rank 8, and then this 9 here has rank 9, and the 12 here has rank 10, and the 15 here has rank 11. Okay, so again, I don't need that entry there. So I'm going to use that now. These the sum of the ranks that correspond to a certain situation for my test statistic. So let me write out here the test statistic. Now I've got a situation. I've got a situation that looks like this. The alternative is a greater than, and so I'm under the situation of 1, and so I need T minus. That's going to be my Wilcoxon sign rank test. T minus here is the sum of the ranks that have negative Q's. Okay. Alright, so my test statistic here is T minus. It's the sum of the ranks that have negative Q's. Okay, so let's see, what does that look like here for my observed test statistic? My observed test statistic here, I need to look where I had negative Q's to begin with. So I had a negative Q, here, 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 and so forth, and here. And so I'm going to add the ranks that correspond to those values. So my observed test statistic here is going to be, what was the rank? I've got a rank of a 3, plus a rank of 7, plus a rank of 5.5, plus a rank of 9, which is 24.5. 0.5. Okay, so that's my observed test statistic. And what I'm going to do, if you look back here to the decision rules, I'm going to reject the null if t is less than or equal to the appropriate percentile from table 6, which describes the distribution of this test statistic here. Yes, and so when I look under table 6, I'm going to look here for a lower percentile. And what we're going to see here is when we make a decision, or we look at our decision rule, just to be complete, we're going to reject H0 if t observed, which is in this case the t minus, is less than or equal to TL, which for this problem is 13. You get this from table 6. So that's a function of the sample size and also the significance level for the Wilcoxon sign rank test. Okay, so looking at our decision here, clearly our observed test statistic is not less than 13. So we fail to reject H0. Okay, and so what does that mean in the context of this problem? How do we interpret this result? What's our interpretation? Well, it's kind of like an inconclusive interpretation almost. We don't really have evidence, so we don't have strong evidence to support the alternative. Now that doesn't mean we have strong evidence for the null either. What it means is that we just didn't have overwhelming evidence to go from the null to the alternative hypothesis, and so it's almost like an inconclusive result. So the interpretation is that we have insufficient statistical evidence to conclude that, let's see here, that firstborns are more aggressive than secondborns according to this study. Okay, so this is an example of the Wilcoxon sign rank test. Again, an alternative to the paired t-test when the assumption of normality does not hold.